Okay, so on derivatives, again, you cannot simply pass the limits inside the derivatives. And we've seen one of these examples already, so this one I'll do a little bit quicker. You could call this the pencil sharpening example, or smoothing out a corner, is that if you take square root x squared plus 1 over n, so what these functions look like is that they look like these smoothed out versions of the absolute value function. And well, as you send n off to infinity, the second part goes away. So that you do get pointwise convergence. And actually, you have uniform convergence also. So uniform convergence doesn't actually save you in this case. And you could think how to prove this. It's quite simple actually to come up with an S. What is the difference between fn of x and x? It's related to this 1 over n. And it doesn't, there is a bound that doesn't depend on x. You have to treat with x equals 0 in one way, and then far away, it's actually a little bit easier to bound that. But okay, but what about the derivatives and differentiability? Well, fn is differentiable. Why? Well, x squared plus 1 over n is strictly positive always and differentiable. And square root of x is differentiable when x is strictly bigger than 0. So f, which is the composition of these two, is also differentiable. So h composed with g is differentiable. And the crucial thing here is that you stay away from x bigger than or equal to 0. And okay, by the chain rule, you can differentiate this. So you get 2x over square root x squared plus 1 over n. The 2 goes away because the 1/2. So x over squared, x squared plus 1 over n. And okay, what is the limit of these? Well, when x is not equal to 0, then there's no problem taking the limit of this denominator, because what you get is x over absolute value of x, which is equal to 1 when x is positive and -1 when x is negative. So-called Heaviside function, in case you know the name. So on the negative side, you have -1. On the positive side, you have 1. But what happens at 0, this limit, is you have to look at it a little bit differently. At 0, f prime n at 0 is always equal to 0. In these pictures, it's a minimum of this function. So the limit f n prime x is actually equal to 0. So you get hole there and fill that hole there, and the top and bottom you get 0. So okay, this limit function is not continuous, and these approximants, what they look like, if you spend some time drawing them, they look something like that. They're becoming sharper and sharper and converging to this Heaviside thing. And actually, and this jump here, what it corresponds to is the fact that f is not, the limit function is not differentiable at 0. Indeed, f prime would be -1 if x is negative, 1 when x is positive, and not defined at x is equal to 0. And it corresponds to the failure in the sequence of this convergence, this uniform convergence, which actually only occurs at 0. But this example is also interesting for many reasons, but one is also that fn prime is actually bounded. So nothing is going off to infinity. Fn prime has absolute value always bounded by 1 for all n and x. It's interpolating between -1 and 1 in some sigmoid fashion. So okay, even with bounded derivative, if you have pointwise convergence, if you have these jumps, you can get problems. Now, second example is also classical. Could be called diminishing waves. So you look at sine nx over n. Let's draw a picture of this. What these look like is that you have these, so when n is equal to 1, you have sine x over 1. So the first function is just regular sine. Now the second function is sine 2x, so it has twice period, something like that. Doesn't really matter exactly how this looks, but twice the period, but half the amplitude as well. And then the third one, fourth one, etc., they have higher and higher periods, but also diminishing amplitude. And one crucial thing with these examples that my picture doesn't really show is that the slopes are always bounded by 1 again. As we will, why? Because somehow the increase in frequency is compensated by a decrease in amplitude. So let's just compute the derivative to see that. Fn prime is n times cosine nx over n. So it's just cosine nx. So indeed, again, just like above, the derivative is bounded by above from 1. But the limit function, what is happening in the limit of this sequence? Well, the amplitudes are decreasing. So this limit function is equal to 0. Namely, well, and it's actually uniformly, well, if we fix an epsilon positive, then we can pick an n bigger than 1 over epsilon. And if n is bigger than n, then fn of x minus 0, the limit function, is less than or well, it's equal to absolute value of sine nx over n, which is less than or equal to 1 over n, which is less than or equal to epsilon by the choice of n. And this holds for all x in real numbers. So this is converging uniformly to 0. And this here crucial thing is that this choice now does not depend on x. But the derivatives don't behave as nicely. So you have these derivatives that oscillate. Now they don't have diminishing amplitude, but they have increasing frequency. But the limit function is also differentiable with derivative equal to 0. So this time you don't lose the derivative in the limit. Everything is differentiable, but the limits just don't behave nicely. Namely, if you take the limit of the derivatives, you get limit of cosine n of x, which does not exist because it oscillates. You can't make it converge, at least for most points. Some points it does converge. And if you take the derivative of the limit, you get 0. So somehow the phenomenon here is that the oscillations are disappearing. Any questions? So this allows the limit function to be differentiable, even though there are sort of wild oscillations in the sequence. And in this case, they are somewhat tame because the derivative is bounded by 1. And then there's a phenomenon here as well that while the derivative here is between -1 and 1, and it's the best estimate that you can have, in the limit, you kind of lose some of that derivative. It goes to 0. So there's some kind of disappearance in this case as well. But why that happens, that's beyond this class to really explain. But it's an important example for many reasons as well. And the final example is related to series that we will properly define on Wednesday, and it's related to probability, actually. I will not prove things here because this is not a probability class. But I will say that this is somewhat related to the Weierstrass function. And it's related to how the derivative actually of the limit function can be bad everywhere. And it's a different type of behavior that's specifically related to series of functions. So let's yi, xi be independent random variables that are normally distributed. You don't have to know what this means necessarily, but if you know, it's nice. I'll give a simulation of what this looks like. And then what you do is you add xi times things that we looked like before. So sine nx over x. So these were the things that for us oscillated kind of weirdly, but you add infinitely many of them with some weights that are random numbers. Now, there's a statement that this sequence converges almost surely. It actually, you can even make it converge uniformly to a function that's the infinite sum, where you just send n to infinity. Now, almost surely means that if you take a random collection of such things, then with probability 1, when you fix these, the convergence happens. And what you get is a limit function. This limit function will be continuous, but it will be continuous, but nowhere differentiable. Nowhere differentiable function. And yet, in the sequence of these functions, if you take finitely many of these terms, this is a very nice sum. This is just a sum of sines and cosines. In other words, is a trigonometric polynomial. Sums of functions are differentiable and continuous, so everything in the sequence is differentiable. But what's happening is that in the limit, that differentiability goes away. And what you get is this oscillating thing. It's closely related to Brownian motion. In fact, it's sometimes called the Gaussian or Brownian bridge, and it can be thought of as Brownian motion conditioned to the fact that at pi, you're equal to 0. So generally, a Brownian motion can increase or decrease, but if you subtract this difference, what you get is an example of Brownian bridge. And actually, you can use this to generate Brownian motion, but I don't want to talk about it now. But I want to show you what this actually looks like. I did a small code of this. In Python, so all this code is doing is it's generating some 1,000 random Gaussian random variables between 0 and 1. It's taking some sampling of time to plot, discretizing everything. It's then computing these functions recursively. So it's taking the previous function and adding the next term in the series. So this f contains within it the functions or the values of the functions for each term in the series. And then it's just plotting them. So let's do that plotting. We'll run for a few seconds. Okay. First, in the sequence, I took a constant 0 function there. Then it adds one sign to it, looking like that. It adds another sign, a third one, a fourth one, fifth one. You see that you get different functions. This is the series partial sums of the series Fn. And okay, the convergence is kind of slow, and the amplitudes of here are very small, so this animation would become quickly not interesting. So I'm skipping, so this is until the 10th step in the series sequence, but then after that, I'm starting to skip with hundreds. So the 100th one is looking like this, or it's already oscillating pretty wildly. If you add another 100 terms, it oscillates a little bit wildly, another 100, etc. And then the pictures start looking very similar because you're adding things of very small amplitude, and the convergence, while it's slow, you've already reached the convergence. You get this function that is oscillating kind of everywhere. It is periodic. 0 at pi, it has the same value, and between it has this behavior that is continuous. This graph you can draw without lifting your pen, but it is nowhere differentiable. So in this shows an extreme example that's related to probability of how to construct a function that is nowhere differentiable as a limit of things that are actually very differentiable themselves. And the problem here that happens is that as you increase the limits, sort of everywhere in the space, you have very big positive derivatives and very big negative derivatives. And these derivatives are canceling each other in such a way that the function doesn't have to blow up. Any questions on this example? Okay, so that's the final example of these that I wanted to present. So these were the bad examples to give you a sense of what can happen even when you have, in some cases, uniform convergence. The limit function can fail in various ways to be integrable. Well, it cannot fail to be integrable, as we will see, but it can fail, the integral can fail to equal its limit of the integrals. And with differentiability, you have a variety of behaviors where the limit can fail to be differentiable at one point, at a whole lot of points, at all the points, or it can fail even if both are fn and f are differentiable, the limits don't have to be the same.